All right, let's dive right in. Today, we're taking a pretty fascinating journey to bridge the gap between abstract software programming concepts and their actual physical hardware execution. I mean, we write code every single day, right? But we rarely stop to visualize the actual physical dance of electrons making the whole shebang happen under the hood.
So before we even touch the bare metal hardware stuff, we kind of have to ask a really fundamental question. Why do we even need data structures in the first place? Sure, it's incredibly easy to just hack together some unstructured code, but what happens when you need to scale that up?
Simply put, data structures are the specific organizational methods that let our programs search massive amounts of data rapidly and handle multiple requests at the exact same time. Think of unstructured code like, dumping all your important documents into a massive, chaotic pile in the middle of your office. Finding one specific tax return, that would literally take hours. Using a predefined data structure is like meticulously organizing a filing cabinet. You aren't just writing cleaner code, you're fundamentally optimizing how the machine physically operates.
Here is our roadmap for this explainer. 1. The power of data structures. 2. Data versus file structures. 3. The von Neumann machine. 4. Mapping arrays to memory. And 5. Compiling and memory allocation.
Section 1. The power of data structures. Why organization matters. Queues, linked lists, trees, graphs, these definitely aren't just arbitrary shapes we draw on whiteboards. Just like an online dictionary uses a highly specific structure to pull up definitions instantly, different data structures are uniquely suited to solve different, complex problems. I mean, you absolutely wouldn't use a hammer to drive a screw, right? It's just the wrong tool for the job. By choosing the correct underlying structure right from the start, you bypass the need to frantically reorganize data on the fly, which lets the processor concentrate purely on getting you your output.
Section 2. Data versus file structures. Memory location matters.
But where exactly does this data live when we're actively running our apps? The crucial thing to understand here is the massive difference in location and speed. Data structures exist entirely in the fast, temporary main memory, your RAM. Think of RAM like a master chef's cutting board. It's right there in front of them, it's lightning fast to use, but it's temporary. File structures, on the other hand, organize data in slower, permanent secondary storage, like your SSD. That's essentially the deep freeze pantry down the hall. It's slower to get to, sure, but it's permanent, and it's built specifically to maximize long-term storage.
Section 3. The von Neumann machine. 1945 architecture model.
To really grasp how main memory handles this data, we've got to zoom way back to John von Neumann's genius 1945 architecture, which, amazingly, still powers almost every modern computer today. This architecture uses a single, shared memory for both your program instructions and your actual data. And this memory is intimately connected to the CPU via specialized communication pathways called buses. You've got the address, data, and control buses. They essentially act as the computer's nervous system, firing precise signals back and forth between the memory and the processor.
Right inside that CPU block, three main components are doing the absolute heavy lifting. First, the control unit directs the traffic, acting kind of like a master conductor. Next, the arithmetic logic unit, or ALU, crunches the math and handles logical comparisons. And finally, you have a series of registers, things like the program counter and the accumulator. Registers are super critical to understand because they're literally the fastest memory in the entire machine. They're the absolute final destination for your code, acting as the processor's ultra-fast, immediate workspace in the exact nanosecond before it turns into pure math.
But there's a catch. This brilliant foundational design has a major, unavoidable limitation known in the industry as the von Neumann bottleneck. Because instructions and data share the exact same bus pathway, instructions can only be executed one at a time, sequentially. If your data is disorganized, it will severely choke the CPU's performance. In fact, modern CPUs are so absurdly fast that they actually spend the vast majority of their lives essentially twiddling their thumbs, just waiting for data to travel from the RAM.
Section 4. Mapping arrays to memory. Defeating the bottleneck.
Because of that physical hardware bottleneck, understanding how your data mathematically maps to physical memory is absolutely crucial. Take a linear array, for example. Each specific value is assigned a sequential byte address in physical memory, starting from one single initial base address. It's kind of like finding a house on a street. If you know the street starts at number 1000 and you need the third house, you don't go knocking on every single door, right? You just add 3. When your code looks up an index, the hardware does a rapid-fire calculation using that base address and the offset to instantly fetch the data. Predictability defeats the bottleneck.
And honestly, it gets even cooler when you look at a 2D matrix. Physical memory isn't a grid at all.
it's a straight line, so the computer literally has to flatten your grid into a 1D sequence, either row by row or column by column. And this fundamentally changes how the hardware accesses your data. If your software loops through data by columns, but it's physically stored in a row major format, well, the CPU has to jump around wildly in physical memory. That causes massive cache misses, completely wrecking your performance efficiency.
Section 5. Compiling and allocation. Code to machine execution. Okay, so we see how data maps to the hardware. Now let's zoom out a bit and look at the compilation process, how we actually turn our human-readable code into physical machine instructions. In a language like C, making an executable is a strict 4-step pipeline. First up, the preprocessor expands the source code and handles your included files. Second, the compiler translates all that expanded code into a low-level assembly language. Third, the assembler takes that assembly and generates raw object code. And fourth, the linker connects those objects with external libraries to finally produce the executable code your operating system can actually run.
Think about it. That beautiful, high-level syntax you spend hours perfectly indenting on your screen, it's kind of a mirage. Ultimately, every single elegant tree, linked list, and object-oriented class you design gets violently stripped away into pure binary strings of ones and zeros. And this raw binary is the absolute only language those CPU registers can actually consume and execute.
Now Java takes a slightly different architectural path to get to the same destination. Instead of compiling all the way down to native machine code right off the bat, it compiles your source code into an intermediate bytecode. Then a Java virtual machine, or JVM, steps in and interprets that bytecode for whatever specific host system it happens to be running on. This is the heart of that famous write once, run anywhere philosophy. It allows your exact same data structures to run smoothly across Mac, Linux, or Windows without ever having to rewrite the core app.
Once these compiled programs actually fire up, they grab memory in two vastly different ways: stack memory and heap memory. The stack is for strict static memory allocation that happens right at compile time. Think of it like a rigid stack of cafeteria trays, highly organized and strictly last in, first out. The heap, on the other hand, is for dynamic memory allocation that happens on the fly at runtime. It's much more like a massive open warehouse where you can just grab whatever empty shelf space is available when you aren't exactly sure how much data you're going to need up front.
Check this out. The stack and the heap actually share the exact same physical address space inside your RAM. They literally sit at opposite ends, actively growing towards each other as your program continuously spins up and manages its data structures. It's this incredible dynamic balancing act happening under the hood thousands of times a second. And here's a fun fact. Because they grow toward one another in that shared space, if they ever accidentally crash into each other, your program instantly fails. That specific catastrophic collision, that's exactly where the famous term Stack Overflow comes from.
We've journeyed all the way from abstract software paradigms right down to the physical reality of CPU registers and memory layout. So the next time you casually type out a line of code to declare a simple array, ask yourself, do you truly know what you're demanding of the physical machine? Or are you just hoping the hardware can cover up your messy data? See you next time.